Hello friends, in mathematics and science, we often write functions as an infinite polynomials like C0 plus C1x plus C2x square plus etc. plus Cn x power n plus etc. where C0, C1 etc. are some scalars and x is a variable. We call this expression as power series because they are defined as an infinite series of powers of some variable, in our case x. A power series may be thought of as a polynomial with infinitely many terms, and in other way any polynomial can be treated as a power series with only finitely many non-zero coefficients. Like polynomials, power series can be added, subtracted, multiplied and differentiated to get new power series. In this session, we describe power series in the variable x. If you give values to the variable x in a power series, we get a series of numbers. We know that an infinite series of numbers may converge or diverge. But for a power series in x, it will always converge at least for some particular value of x, namely x equal to 0. In this session, we will show that the set of points at which a given power series converges is always an interval. It may be too short to contain only one point, or it may be too large to contain all real numbers. We proceed with the precise definition of an infinite series. A power series in x is a series of the form summation Cn x power n from 0 to infinity, which is equal to C0 plus C1x plus C2x square plus etc. plus Cn x power n plus etc. equation number 1. Where C0, C1, C2 etc. are constants and x is a variable. Some examples of power series are summation x power n from 0 to infinity, which is equal to 1 plus x square plus etc. plus x power n plus etc. Summation negative 1 power n minus 1 into x power 2n minus 1 upon 2n minus 1 where n from 1 to infinity, which is equal to x minus x cube upon 3 plus x power upon 5 minus etc. Summation x power n upon n factorial where n from 0 to infinity, which is equal to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus etc. Summation n factorial into x power n from 0 to infinity, which is equal to 1 plus x plus 2 factorial into x square plus 3 factorial into x cube plus etc. We know that an equation involving one dependent variable and its derivative with respect to one or more independent variable is called a differential equation. For example, dy upon dx equal to cos x is a differential equation. A function y equal to g of x is called a solution of a given differential equation on some interval, say a less than x less than b, perhaps infinite, if g of x is defined and differentiable throughout that interval and is such that the equation become an identity when y and dy upon dx are replaced by g and g prime respectively. For example, y equal to sin x is a solution of the differential equation dy upon dx equal to cos x. In this example, the differential equation has a solution y equal to sin x, which is an elementary function. This may not be the situation in general. A differential equation does not have a solution in terms of elementary function, but it may have a solution in terms of a power series. The interval and radius of convergence. We know that a series of real numbers is useful only if it is converges. Any power series will give us an infinite series of numbers as we chose a particular value for the variable. The convergence of the power series will depend upon the values of x that we put into the series. A power series may converge for some values of x and not for other values of x. So, the natural question is, for what values of x will a given power series converge? We first observe the following. The power series summation Cn x power n from 0 to infinity always converges at x equal to 0, since substituting this value produce the series C0 plus 0 plus 0 plus etc. plus 0 plus etc. which converges to the constant term C naught. The power series summation x power n, n from 0 to infinity equal to 1 plus x square plus etc. plus x power n plus etc. does not converge at x equal to 1, since substituting this value produces the series 1 plus 1 plus 1 plus etc. plus 1 plus etc. which is divergent. Based on the above observations, we note that if a numerical value is substituted for x in a power series, summation Cn x power n, n from 0 to infinity, then the resulting series of the number may either converge or diverge. This leads to the problem of determining the set of x values for which a given power series converges. This is called its convergence test. Theorem 1. Convergence test of power series. For any power series, summation Cn x power n, n from 0 to infinity equal to C naught plus C1x plus C2x square plus etc. plus Cn x power n plus etc. exactly one of the following is true. First one, the series converges only for x equal to 0 and hence diverges elsewhere. Second one, the series converges absolutely and hence converges for all real values of x. Third one, there is a positive real number r depending on the particular series such that the series converges absolutely and hence converges for all x in the finite open interval negative r and diverges if x less than negative r or x greater than r. At either of the endpoints x equal to negative r or x equal to r, the series may converge absolutely, converge conditionally or diverge depending on the particular series. Theorem 1 states that the convergence set for a power series in x is always an interval centered at x equal to 0, possibly just the value x equal to 0 itself or possibly infinite. For this reason, the set of points at which the power series in x converges is called the interval of convergence. If a power series in x converges only at x equal to 0, then the interval of convergence is singleton set 0, and we say that the radius of convergence is 0. If a power series converges for all values of x, then the interval of convergence is open interval negative infinity, positive infinity, and we say that the series has radius of convergence positive infinity. If a power series has the interval of convergence open interval negative r, positive r, we say that the series has radius of convergence r. Ratio test for finding the interval of convergence. For finding the interval of convergence of power series, we apply the ratio test for absolute convergence of series. This process involves two steps. Step 1, use the ratio test to find the interval where the series converges absolutely. Step 2, if the interval of absolute convergence is finite, test for convergence or divergence at each endpoints. As an illustration of this test, we find the interval of convergence and radius of convergence of the following power series. First one, we apply the ratio test for absolute convergence. Here nth term of the series is un equal to x power n. We have rho equal to limit of absolute value of un plus 1 upon un as n approaches infinity, which is equal to limit of absolute value of x power n plus 1 upon x power n as n approaches infinity, which is equal to limit of absolute value of x as n approaches infinity, which is equal to absolute value of x. Hence, the power series converges absolutely if rho equal to absolute value of x strictly less than 1 and diverges if rho equal to absolute value of x greater than 1. The test is inconclusive if absolute value of x equal to 1, that is if x equal to 1 or x equal to negative 1, which means that we will have to re-investigate convergence at these values separately. If x equal to 1, the series become summation 1 power n, n from 0 to infinity, which is equal to 1 plus 1 plus 1 plus etc. plus 1 plus etc. which is divergent. If x equal to negative 1, the series become summation negative 1 power n from 1 to infinity, which is equal to 1 minus plus etc. which is also divergent. Thus, the set of points at which the given power series converges is open interval negative 1 1, that is the interval of convergence is open interval negative 1 1. Hence, the radius of convergence is r equal to 1. Second one, the series summation x power n upon n factorial where n from 0 to infinity equal to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus etc. is called the exponential series. In the next session, we will find this as a Maclaurin series of the exponential function e power x, and we will write e power x equal to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus etc. plus x power n upon n factorial plus etc. Applying the ratio test for absolute convergence with the un equal to x power n upon n factorial, we obtain rho equal to limit of absolute value of un plus 1 upon un as n approaches infinity, which is equal to limit of absolute value of x power n plus 1 upon n plus 1 factorial into n factorial upon x power n as n approaches infinity, which is equal to limit of absolute value of x upon n plus 1 as n approaches infinity, which is equal to absolute value of x into limit of 1 upon n plus 1 as n approaches infinity, which is equal to absolute value of x into 0, which is equal to 0. Since rho equal to 0 less than 1 for all x, the series converges absolutely for all x. Thus, the interval of convergence is open interval negative infinity, positive infinity, and the radius of convergence is r equal to positive infinity. As observed above, the series summation x power n upon n factorial as n from 0 to infinity is the exponential series. The above discussion shows that radius of convergence of the series representation of e power x is positive infinity and the interval of convergence is open interval negative infinity, positive infinity. In other words, the exponential function e power x is defined at every real number. Next one, the power series summation n factorial into x power n where n from 0 to infinity always converges at x equal to 0. Since substituting this value produce the series 1 plus 0 plus 0 plus etc. plus 0 plus etc. If x not equal to 0, applying the ratio test for absolute convergence with the un equal to n factorial into x power n, we obtain rho equal to limit of absolute value of un plus 1 upon un as n approaches infinity, which is equal to limit of absolute value of n plus 1 factorial into x power n plus 1 upon n factorial into x power n as n approaches infinity, which is equal to limit of n plus 1 into absolute value of x as n approaches infinity, which is equal to absolute value of x into limit of n plus 1 as n approaches infinity, which is equal to infinity. Therefore, the series diverges for all non-zero values of x. Thus, the interval of convergence is a single value x equal to 0 and the radius of convergence is r equal to 0. Next one, with the un equal to negative 1 power n minus 1 into x power n upon n, we obtain rho equal to limit of absolute value of un plus 1 upon un as n approaches infinity, which is equal to limit of absolute value of x power n plus 1 upon n plus 1 into n upon x power n, which is equal to absolute value of x into limit of 1 upon 1 plus 1 upon n as n approaches infinity, which is equal to absolute value of x into 1, which is equal to absolute value of x. The ratio test for absolute convergence implies the series converges absolutely if absolute value of x less than 1 and diverges if absolute value of x greater than 1. the test is inconclusive if absolute value of x equal to 1. That is, if x equal to 1 or x equal to negative 1, which means that we will have to investigate convergence at these values separately. If x equal to 1, the series become 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus etc., which is the divergent alternating harmonic series and is convergent if x equal to negative 1. The series become negative 1 minus negative upon 2 plus 1 upon 3 minus 1 upon 4 minus etc. A scalar multiple of the divergent harmonic series 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4 plus etc., and hence it diverges. Thus, the set of points at which the given power series converges is set of all x belongs to R such that negative 1 less than x less than or equal to 1. That is, the interval of convergence is left open right closed interval negative 1 1. Hence, the radius of convergence is R equal to 1. Next one, rho equal to limit of absolute value of un plus 1 upon un as n approaches infinity, which is equal to limit of absolute value of 2n minus 1 upon 2n plus 1 into x square as n approaches infinity, which is equal to x square into limit of 2n minus 1 upon 2n plus 1 as n approaches infinity, which is equal to x square into limit of 2 minus 1 upon n upon 2 plus 1 upon n as n approaches infinity, which is equal to x square into 1, which is equal to x square. The ratio test for absolute convergence implies the series converges absolutely for x square less than 1, that is for negative 1 less than x less than 1. It diverges for x square greater than 1, that is for absolute value of x greater than 1. At x equal to 1, the series become 1 minus 1 upon 3 plus 1 upon 5 minus 1 upon 7 plus etc., which converges by the Leibniz test or alternating series test. It also converges at x equal to negative 1 because it is again an alternating series that satisfies the condition for convergence. The value at x equal to negative 1 is the negative of the value at x equal to 1. Hence, the series converges for negative 1 less than or equal to x less than or equal to 1, and hence the interval of convergence is closed interval negative 1 1 and the radius of convergence is r equal to 1. Power series in x minus x naught. Definition: a power series about x equal to x 0 or a power series in x minus x naught is a series of the form summation Cn x minus x naught whole power n where n from 0 to infinity, which is equal to C naught plus C1 into x minus x naught plus C2 into x minus x naught whole square plus etc. plus Cn into x minus x naught whole power n plus etc. Equation number 2, in which the center x naught and the coefficients C naught, C1, C2 etc., Cn etc. are constants. The power series summation Cn x power n from 0 to infinity equal to C naught plus C1x plus C2x square plus etc. plus Cn x power n plus etc. is a power series with a center at 0. Theorem 2, convergence test of power series. For a power series, summation Cn x minus x naught whole power n where n from 0 to infinity, exactly one of the following is true. First one, the series converges only for x equal to x naught and hence diverges elsewhere. Second one, the series converges absolutely and hence converges for all real values of x. Third one, there is a positive real number r such that the series converges absolutely and hence converges for all x in the finite open interval x naught minus r, x naught plus r, and diverges if x less than x naught minus r or x greater than x naught plus r. At either of the endpoints x equal to x naught minus r or x equal to x naught plus r, the series may converge absolutely, converge conditionally or diverge depending on the particular series. Theorem 2 states that the convergence set for a power series in X is always an interval centered at x equal to x naught, possibly just the value x equal to x naught itself or possibly infinite. The set of points at which the power series in X converges is called the interval of convergence. If a power series in X converges only at x equal to x naught, then the interval of convergence reduces to the single value x equal to x naught, and we say that the radius of convergence is 0. If a power series converges for all values of x, then the interval of convergence is open interval negative infinity, positive infinity, and we say that the series has radius of convergence positive infinity. If a power series has the interval convergence open interval x naught minus r, x naught plus r, we say that the series has radius of convergence. Now, we find the interval of convergence and radius of convergence of the series summation x minus 3 whole power n upon n square where n from 1 to infinity. For this, we apply the ratio test for absolute convergence. We have rho equal to limit of absolute value of un plus 1 upon un as n approaches infinity, which is equal to limit of absolute value of x minus 3 whole power n plus 1 upon n plus 1 whole square into n square upon x minus 3 whole power n as n approaches infinity, which is equal to limit of absolute value of x minus 3 into n upon n plus 1 whole square as n approaches infinity, which is equal to absolute value of x minus 3 into limit of 1 upon 1 plus 1 upon n whole square as n approaches infinity, which is equal to absolute value of x minus 3. Thus, the series converges absolutely if absolute value of x minus 3 less than 1, or negative 1 less than x minus 3 less than 1, or 2 less than x less than 4. The series diverges if x less than 2 or x greater than 4. To determine the convergence behavior at the endpoints x equal to 2 and x equal to 4, we substitute these values in the given series. If x equal to 4, the series is summation 1 power n upon n square where n from 1 to infinity, which is equal to summation 1 upon n square n from 1 to infinity, which is equal to 1 plus 1 upon 2 square plus 1 upon 3 square plus etc., which is a convergent P series with P equal to 2. If x equal to 2, the series is summation negative 1 power n upon n square where n from 1 to infinity, which is equal to minus 1 plus 1 upon 2 square minus 1 upon 3 square plus etc. Since this converges absolutely, the interval of convergence of the given series is closed interval 2, 4. Since 3 is the midpoint of the interval, the radius of convergence is r equal to 1. Is a power series a function? Does it make sense to think of a power series as a function of x? We investigate this question now. For suppose the power series 1 plus x square plus x cube plus etc. represents a function f of x, we try to evaluate this function at x equal to 0. Then f of 0 equal to 1 plus 0 square plus etc., which is equal to 1. When x equal to 1, f of 1 equal to 1 plus 1 square plus etc. Were the right hand side a divergent series. That means the series does not give a sum. So, f of 1 is not a real number. Hence, the function is not defined at x equal to 1. Recalling that the interval of convergence of the series 1 plus x square plus x cube plus etc. is open interval negative 1, 1, we conclude that the natural domain of the function f of x is open interval negative 1, 1. Functions defined by power series. If a function f is expressed as a power series on some interval, then we say that f is represented by the power series on that interval. For example, since the sum of the geometric series 1 plus x square plus x cube plus etc. is 1 upon 1 minus x for negative 1 less than x less than 1. The function 1 upon 1 minus x is represented by the power series 1 plus x square plus x cube plus etc. on the interval -1 less than x less than 1, and we write 1 upon 1 minus x equal to 1 plus x square plus x cube plus etc. for -1 less than x less than 1. Sometimes new functions actually originate as a power series. For example, the following functions called Bessel's function arise naturally in the study of planetary motion and in various problems that involves heat flow. J naught of x equal to summation -1 power n x power 2n upon 2 power 2n into n factorial whole square where n from 0 to infinity. And J1 of x equal to summation -1 power n x power 2n plus 1 upon 2 power 2n plus 1 into n factorial into n plus 1 whole factorial where n from 0 to infinity. Now, we find the domain of the above Bessel's function. Finding the domain of the above Bessel's function is equivalent to finding the interval of convergence where the power series converge. We apply the ratio test for absolute convergence. We have rho equal to limit of absolute value of un plus 1 upon un as n approaches infinity, which is equal to limit of absolute value of -1 power n plus 1 into x power 2 times n plus 1 upon 2 power 2 times n plus 1 into n plus 1 factorial whole square into 2 power 2n into n factorial upon -1 power n into x power n plus 1 as n approaches infinity, which is equal to limit of x square upon 4 times n plus 1 whole square as n approaches infinity, which is equal to 0 strictly less than 1. Hence, the radius of convergence is positive infinity, that is the series converges for all x, that is the domain of J naught of x is open interval -infinity positive infinity. Similarly, it can be shown that the domain of J1 of x is open interval -infinity positive infinity. In the next session, we will see that the Maclaurin series of the logarithmic function logarithm of 1 plus x is x minus x square upon 2 plus x cube upon 3 minus x power 4 upon 4 plus etc. plus -1 power n into x power n upon n plus etc. Now, we discuss the convergence of the above logarithmic series and the interval of convergence. Let un equal to -1 power n plus 1 into x power n upon n. Then, for a fixed x, limit of absolute value of un plus 1 upon un as n approaches infinity is limit of absolute value of n upon n plus 1 into x power n plus 1 upon x power n as n approaches infinity, which is equal to limit of absolute value of n upon n plus 1 into absolute value of x as n approaches infinity, which is equal to limit of absolute value of 1 upon 1 plus 1 upon n into absolute value of x as n approaches infinity, which is equal to absolute value of x. Since limit of 1 upon 1 plus 1 upon n as n approaches infinity is 1. Hence, the given series is convergent for absolute value of x less than 1, that is when -1 less than x less than 1. At x equal to -1, the series becomes summation -1 power n plus 1 -1 power n upon n where n from 1 to infinity, which is equal to summation 1 upon n where n from 1 to infinity, the divergent harmonic series. At x equal to 1, the series become the convergent alternating harmonic series summation -1 power n plus 1 upon n where n from 1 to infinity. Hence, the interval of convergence is -1 less than x less than or equal to 1 and the radius of convergence is 1. Sum and product of series. We wind up this session with a look at the sum and product of two power series. Given the power series f of x equal to summation Cn x minus a whole power n where n from 0 to infinity, which is equal to C naught plus C1 into x minus a plus C2 into x minus a whole square plus etc. With the interval of convergence, open interval a minus Rf a plus Rf and g of x equal to summation dn x minus a whole power n where n from 0 to infinity, which is equal to d naught plus d1 into x minus a plus d2 into x minus a whole square plus etc. With the interval of convergence, open interval a minus Rg a plus Rg. Then sum of these two series is the power series f of x plus g of x equal to summation Cn plus Dn into x minus a whole power n where n from 0 to infinity, which is equal to C naught plus D naught plus C1 plus D1 into x minus a plus etc. with interval of convergence, open interval a minus Rf a plus Rf intersection open interval a minus Rg a plus Rg. The product of the two series is the power series f of x into g of x equal to summation n from 0 to infinity summation n equal to L plus k Ci dk into x minus a whole power n, which is equal to C naught d naught plus C1 d naught plus C naught d1 into x minus a plus etc. with interval of convergence, open interval a minus Rf a plus Rf intersection open interval a minus Rg a plus Rg. Let us summarize the session. In this session, we have described power series in the variable x. We have seen that the set of points at which a given power series converges is either a singleton set or an interval centered at some point and its radius is the radius of convergence of the power series. We discussed methods to identify the interval of convergence of a given power series through several examples. Also, we have described the definition of sum and product of two power series. Hope you enjoy the session. See you next time. Until then, goodbye.